So we're located in the Milky Way galaxy, and we're spiraling around the center. And we are also in our solar system going around the sun. And if we think about the Earth, it's rotating about its axis. And wherever you are right now, you definitely don't feel like you're moving. And so the main question is, why don't you feel like you're moving? And so if you wrestle with that and you think through that, um, the room that you're in, as well as you, are moving according to the frame of reference of the universe. You're moving very, very fast, but because the room is moving and you're moving, it doesn't feel like you're moving. And so when you define anything with distance or speed, you have to look at frame of reference. So frame of reference is a key idea, and so we have to make any measurement of position, distance, or speed has to be made with respect to a frame of reference. And so even though, from the frame of reference of the universe, we're moving quite rapidly, we use our room as a still frame of reference, and we can base things off of that. When we talk about position, it's important to look at position in a couple different ways. We look in one dimension, so we could have positive y-axis, negative y-axis, or positive x-axis, negative x. And we can define our location. We could be somewhere along this line here. We could be somewhere vertically. And then in two dimensions, we bring them both together. So we have positive x, positive y, negative y. And we could be located somewhere in the x-axis and the y as well. And then for three dimensions, positive y, positive x, negative x. And we have the z-axis. So for our purposes, we won't need the third dimension very much until we look at things in magnetism. But this would be out and then over and up. So it could be in three places, but we're mostly going to be concentrating on 1 and 2 dimensions. When we talk about distance and displacement, when you think about distance, that's the total length of the path traveled by a particle. And this is like a length of course in a race. So your car has an odometer, and that will show basically how far you've gone. It doesn't know anything about direction. And this is in contrast to displacement. That is where you look at the starting position and the finishing position. And the way we calculate that is we look at the change in, and this is the Greek letter delta, change in x means the change in position. So we take the final position minus the initial position, and we can determine our location. So let's go ahead and establish a problem to practice this. So we can draw our situation here. Person is starting at 0 meters. They go to positive 12 meters, and then they walk back to positive 9 meters. And we want to find their distance and find their displacement. So distance, we add up the total length traveled. So 0 all the way to 12 plus another 3. And that would give us a total distance of 15 meters. But displacement, when we establish that, that's final position minus initial position. Final position is positive 9. Initial position is 0. And we get a displacement of positive 9 meters. So we look at where we started to where we finished. Here's another instance that we can compare and contrast distance and displacement. So if we started at position A and went around the track and ended at position B, the total distance would be 100 meters, but the displacement would be from where you start to where you finish, and that would be 50 meters up the page or north if we established a direction. So with displacement, we must have direction. So why don't you try this one? Go ahead and draw out the situation and try to calculate the distance traveled by the particle and the displacement using the equation. So the distance is 2 meters. We started at 1 meter and then went back to -1. And then for the displacement, that's the final position, which is -1, minus the initial position, which is 1. So the displacement is 2 meters.
Okay, now for this one, draw out the car, and the car starts at -3, goes to +8, then goes to -7. And enter in what you believe the distance is and what the displacement is. Make sure you draw it out first and then calculate. So the car starts at -3, then goes to 8, and then back to -7. And so to get the distance, we can count up the total. There first 3, then another 8, which is 11, plus 8, which would be 19, and plus another 7 would be 26. And then the displacement is the final position, -7 minus the initial position. So the displacement from here to here is -4. Next, we'll try one where we're driving around a circular track. So we'll first go ahead and draw that. We have a diameter of 40 meters, and the radius therefore is 20. And if we assume the car starts at the bottom, the car goes around 2.5 times, and we want to figure out how far the car is driven and determine that, and then also determine the displacement. And I gave you a hint up here at the top. So why don't you go ahead and try this one and enter in your values for the distance and displacement. So the distance for one time around is the circumference, 2 pi r, which is 125.66. And therefore 2.5 times that would be, we would get twice around and then another half. So 314.16 is the distance. And then displacement is where we start to where we finish. So if we started here and we finished up here, the displacement is 40 meters north or 40 meters up from the start.